Welcome to Chapter 12. In Chapter 12, we're going to switch gears a little bit and talk about states of matter. So this is video number 1. So when we're talking about states of matter, underlying all of our states of matter, which we normally think of as solids, liquids, and gases, we're going to be talking about the kinetic molecular theory. So what the kinetic molecular theory does is it explains the different properties of solids, liquids, and gases based on their atomic composition. Kinetic, movement, molecular, molecules. So what we're going to be doing is we are going to be talking about how the movement, I don't know why that M won't work, of the molecules make something a gas, or make something a solid, or make something a liquid. So we talk about on the atomic and particle level. So the kinetic molecular theory describes the behavior of matter in terms of particles in motion. So there are 3 basic assumptions of the kinetic molecular theory, and you will need to know these 3. The first assumption is that gases consist of small particles separated by empty space. So number 1, the gases are composed of small particles separated by empty space. Remember, Aristotle said empty space couldn't exist. Democritus said, yeah, it can. And later on in the 1800s, we proved that empty space could exist through scientific experiments. This is because, why is there that empty space? Gas particles are so far apart, because they're so far apart, they're not going to be really attracted to each other or repelled by each other. So it's kind of like, if you live in the city, you're not like a gas particle. You live right next to your neighbor. But if you live out in the country and it's 10 miles between your house and your neighbor's house, y'all probably aren't going to bother each other very much because you're so far apart you can't be significantly attracted to each other or repelled by each other. Our second assumption is that gas particles are in constant random motion. That means they are constantly moving all the time. And they have elastic collisions. What that means, elastic is like if you take your gym shorts and you stretch the band, the waistband, it's going to pop back to where it was supposed to be. Elastic means that you don't lose any energy. What this means is that gas particles, since they're in constant random motion, they're going to actually move in straight lines until they collide with something and they bounce off. So this is kind of like when I was growing up, my grandparents had a dog, and her name was Auburn, War Eagle, and Auburn was blind. She was really old. And Auburn would run in straight lines until she bounced off something. So she'd just run and she'd bounce off the couch, or she'd bounce off the TV stand, or she'd bounce off the wall. Not hard, but she was blind and she liked to run around and she was old. Gas particles are kind of like that. They're going to move all the time because they're in constant random motion. And when they hit something, they're going to collide, they're going to bounce off and move in the other direction. So, elastic collisions, it's one when you do not lose any kinetic energy. So remember that a law of conservation of mass states that mass can neither be created nor destroyed. It can only be conserved. The same thing with energy. Energy can neither be created nor destroyed. It can only be transferred. And one of the ways that we do that is through elastic collisions. And our third part of the kinetic molecular theory is that particles have kinetic energy. Well, what is kinetic energy? You said it's movement of energy. So it's when something is moving, that's its kinetic energy. We're not going to worry about the mass times velocity squared divided by 2 to calculate kinetic energy. But one thing I want you to know is how we measure kinetic energy is the temperature. So if I take the temperature of something, so say I stick a thermometer in a glass of water and it registers the temperature as 21 degrees Celsius. What that tells me is that is the average kinetic energy. Remember, kinetic energy is movement, or how fast something is moving, of the particles in a sample of matter. So think about it this way. When it snows, outside the temperature is low. Okay? When the temperature is low, that means the particles move slowly, so the water particles stick together and form snow. If it's warmer outside, that means the kinetic energy of the particles are moving faster. That's why you have a higher temperature. And you don't have snow because they aren't sticking together because they're moving too fast. So, temperature measures kinetic energy of the particles. Most of the time we talk about temperature when we're talking about the air, and that's just measuring the gas particles in the air. So, when we're talking about the kinetic molecular theory, it mainly deals with gases and the fact that gases flow easily because they aren't really attracted to each other. Because of this, they can diffuse from one material through another. So this is kind of like if you had a strainer and you are straining pasta. Well, pasta's been in the boiling water to cook it. When you're done cooking it, you pour the water out, and the water moves from one material through another. Diffusion is where it goes through the material. Effusion is where it escapes through a tiny opening. So effusion is like when you poke a hole in a balloon. And the balloon deflates. Diffusion with a D is when the balloon takes 4 months to deflate slowly through diffusion, where the air moves through that latex balloon, but it takes it a really long time to do so. Effusion means you got a hole somewhere. So, going back to the kinetic molecular theory, you know that you have lots and lots of space between gas particles. Because of that, you can compress gases. And when you compress something, that's going to reduce the empty space between the particles. Gases can be compressed. We'll talk more about liquids and solids later on. So when we're talking about compressing a gas, if you go back to this visual right here, if this is where I'm starting, if I compress that gas and move towards the left, I am going to make the space between the particles much smaller. That's going to increase the pressure. There's more force per unit area because the area has gone down. So gas particles exert pressure when they collide with the walls of their container. And if you compress something, then it's going to end up exerting more pressure on the walls of the container because there's more gas particles in that smaller space. Think about like a trash compactor. When you compact the trash, they're going to have less space, so they're going to start running into each other more. And then you've also probably heard of air pressure. Air pressure is the Earth's atmospheric pressure, and it goes on in all directions. When you go higher, so like if you flew to Denver, or if you just get in an airplane and take off, there's less air pressure at high altitudes because there are fewer particles present. And there are few particles present because the force of gravity is less. This is why you can cook something faster in Denver than you can in Nashville. Because in Denver, that when you cook something at altitude, it's going to take a different amount of time than it would when you're at sea level because there is less air molecules, and so you're going to have to find more air molecules. You're going to have to work harder to make them heat up if you're in Denver, which is a mile above sea level. So this is why the U.S. Olympic Training Facility is in the Rocky Mountains, because if you train where there's less air molecules to breathe, then it's going to be easier for you when you go down the mountain. So how do we measure all of this? We use what's called a barometer. It was invented by Torricelli, and a barometer is an instrument used to measure atmospheric pressure. And if you look at this right here, so right here, we've got a bowl and it's full of mercury. Mercury also goes up into this tube, and that is our barometer. So when the atmospheric pressure pushes down on the mercury in the bowl. The only place the mercury can go is up into the tube. So if you've ever heard of the meteorologist on the news saying, oh, the mercury is rising or the mercury is falling, this is what they're talking about. If the atmospheric pressure is greater and it's pushing down on the mercury, then the mercury is going to rise in the column. If the atmospheric pressure is less, so it's not pushing down on the mercury, then the mercury will fall, and you use a barometer to do that. Barometers are typically measured in millimeters of mercury, or in torr, and that is named after Torricelli, who invented the barometer. We can also use manometers, and they measure gas pressure in a closed container, but we're mostly going to be using barometers. That's what you use in meteorology. So when we were talking about the SI unit of force, that is the Newton. You'll talk more about that in physics. But we are going to talk about pascals. Pascals are equal to the force of 1 Newton per square meter. We're also going to talk about atmospheres. So the main thing that you need to know is we measure atmospheric pressure in atmospheres. So 1 atmosphere is mathematically equal to 760 millimeters of mercury. That comes from my barometer. And with the SI system, that is also equal to 101.3 kilopascals. So those are just 3 numbers, 3 different standards of measurement that all they mean the same thing. Kind of the way that we use Fahrenheit, but the rest of the world uses Celsius. We're going to use atmospheric pressure, ATMs. But in Europe and other places, they may use kilopascals, and meteorology is going to use millimeters of mercury. So here are all those different things. You've also probably heard of PSI. And PSI is pounds per square inch, and we use that in our tires on our cars. So, where does all this come into play? Is Dalton's law of partial pressures, and this is going back to the pressure of different gases, is that the total pressure of a mixture of gases is equal to the sum of the pressures of all the gases that are mixed up. So basically what that means is that we look at the partial pressure, we take into account the number of moles, the size, the temperature. You don't really worry about what type of gas it is. So, if I'm looking at this formula, it's going to be the P total is equal to P of 1 plus P of 2 plus P of 3 plus ... until you're done with all of yours. So let's look at an example problem. And we can calculate the amount of gas produced in a chemical reaction. So here's our example. A mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. What is the partial pressure of oxygen if the partial pressure of carbon dioxide is 0.7 atmospheres and oxygen is 0.12 atmospheres? So here's the first thing I'm going to do, is I'm going to write that I've got pressure of oxygen plus pressure of carbon dioxide plus pressure of nitrogen equals my total pressure. I set it up. That all comes from the first sentence. Then I'm going to plug in some numbers. Well, my total pressure is 0.97 atmospheres. And then it says, what is the partial pressure of oxygen? That's X. If the partial pressure of carbon dioxide is 0.7 and nitrogen is 0.12. So I can plug this in and solve for my unknown. I'm going to add my like terms. So this is going to be X plus 0.82, that is also in atmospheres, is equal to 0.97 atmospheres. To get X by itself, I'm going to subtract on both sides. Sorry, that should be a 0. And I get 0.15 atmospheres. And that is Dalton's law of partial pressures. Thanks so much for watching video 1.